temporal dynamics of oscillatory synchronization in human basic ganglia. And when preparing this talk, I thought of how to integrate this in this very broad topics of the data week. And I thought that maybe my experience with a very specific modality in neuroscience might serve to even those who don't work with neurophysiology as examples of multidimensionality in neurophysiological data, and to, oops, sorry, doesn't move. Okay, and to integrate this one mode into all the multimodal or the multiple modalities in neuroscience, I thought of a picture how to localize this modality that is neurophysiology. And I came up with this river analogy. So if you have a river in a country, so here it's the Amazonas that even flows through several countries, then you might think of MRI or DTI as roadmaps of this river, as roadmaps of the brain that gives you structural information. But you can also use imaging to get some functional information about, for example, the flow directions of the river, but those are rather, let's say, slow because of the slow or the low frequency sampling rate of functional imaging. So it's functional imaging wouldn't be able to capture really fast mechanisms of the brain, fast mechanisms that allow us to have reaction times of, let's say, 600 milliseconds, or a neuronal firing rates that are approximately 200 hertz. So within this river analogy, I thought about how, when you look deeper in the river, for example, in the Amazonas, what you can observe is the Poroca phenomenon. I didn't know that before, but apparently there can be waves that are created within the river that spread to the coast side. And of course, this leads us to the image of brain waves that we can record with electrophysiology, with neurophysiology, because in electrophysiology you have really high sampling rates, which allows you to capture current fluctuations in the brain, which then gets you closer to the temporal resolution that is needed in neural processing. And there are different sorry, I will just move this. Yeah, okay. There are different modalities in neurophysiology. I will briefly introduce 3 of them. So first you have the EEG. This would be sensors that are widely distributed across along the coast side of the river, and that allow you to capture brain waves from the outside, right? So you would mainly capture cortical brain waves. And then you have ECOG recordings that still remain on the surface, but you slightly enter more into the river, and you get a higher resolution while capturing only a smaller population or a smaller part of the river. And then you have local field potentials that also capture current fluctuations, but of an even smaller neuronal population that might be deeper in the brain or deeper in the river. And in the last years, my main yeah, then okay, then you also have intracellular recordings, but I won't talk too much about those, and these would be the equivalent of the water molecules. But in the last research, in my last years of research, I mainly focused on those local field potential recordings, so on recording current fluctuations around neuronal assemblies that are located deep within the brain. So I want to talk about this one modality in neuroscience that not a lot of researchers maybe apply, but still this one modality has already multiple dimensions. So in my specific context, I'm working with local field potentials that are recorded in a very specific area of the brain, that is the subthalamic nucleus, which is part of the basal ganglia. It's very, very small. And why do we record local field potentials there is because stimulating or applying current to this specific brain area alleviates motor symptoms in Parkinson's disease patients. So it's human data that I'm talking about. And Parkinson's disease is a movement disorder, and here I already introduced the first dimension of this one modality, that is in this case the fact that Parkinson's disease patients have a lack of dopamine. So it's a neurodegenerative disease where the substantia nigra degenerates, and therefore the patients have less dopamine in their central system, so in their basal ganglia. But you can alleviate the symptoms not only by the brain stimulation, but also by taking dopaminergic medication. So you have, when recording from this very small area in the brain, you can have two states, two dimensions, that is either without medication, so the absence of dopamine, or with medication. That would be then the on state when you substitute dopamine into the system. And then in my research, I mainly added another dimension that would be whether you record your activity while the patient is at rest or while he or she is moving. So here already in one modality, you can introduce several dimensions that would be medication, either with medication or without medication, with or without dopamine, and movement, either at rest or being at movement. Okay, but now let's first talk a bit about the signal that we're recording. So the local field potentials, the brain waves that show current fluctuations that seem to be two-dimensional, right, at the first sight, because you have time, the brain wave is moving over time, and you have the amplitude of the brain wave, so it fluctuates in the amplitude of the current. But you can decompose this signal and then add another dimension. So additionally to your domain time and amplitude, you can decompose this first signal that you see here in red, where you have this fluctuating amplitude, into different frequencies. So within this red signal, you have a very slow frequency, for example, that would be this blue line. And then you have also added up here faster frequencies that would be here, this lila, violet, I don't know what the name is in English, line. So within this two-dimensional signal, you can add a third dimension that would be the frequency domain. And for each frequency, again, you have different amplitudes, right? For example, here the slow frequencies, they have rather high amplitudes, while the higher frequencies, they have low amplitudes. So we have already 5 dimensions now in the data that I will talk about. And another way of visualizing this 3-dimension in a 2-dimensional plot is the type frequency plot. And here actually you have the time scale on the x-axis and the frequency scale on the y-axis. So the frequency decomposition in 1 Hertz steps is visualized here from around 5 Hertz to 30 Hertz. And color-coded is then the amplitude, the thing that you see here. And what you can also already perceive here is that warm colors, so yellow would be very high amplitudes and blue would be lower amplitudes. So continuing with this data trace that was recorded at rest. So we have a patient that is at rest that didn't take any dopaminergic medication. So it's the pathological system. And if we add then dopaminergic medication to the system, we can already look at this raw data trace and ask ourselves, okay, what difference do we see, right? Because in research, you always observe something and then maybe you get ideas from the data, what might have influenced the data or what might change the data. And here, for example, you can, on this very small trace of a couple of seconds, see that there might be something happening here in this frequency range. So in the off medication state, without dopamine, there seem to be high amplitudes scattered in the frequency range that we call beta frequency range, from 13 to 30 hertz, but specifically in the low beta range from 30 to 20 hertz, that you don't observe anymore as soon as the patient gets or takes medication. And what you might then do to reduce your dimensions and to try to assess this observation that you have is to reduce from 3 dimensions to 2 dimensions by averaging over time. So you lose your time domain, and you're just looking on average over the entire recording. Is the amplitude different from our frequencies in the on than in the off medication state? And it is statistically significant across those 99 patients that this observation that you had in your raw data is actually observable across all patients when you average over time. That is, the amplitudes of the signal in the beta frequency range are reduced by dopaminergic medication. And if you then reduce another dimension by averaging over this frequencies that might be relevant in this specific observation, so by averaging over frequencies, then you get 1 dimension left for 1 patient, right? So dopaminergic, absence of dopaminergic medication, and then averaged over the entire recording and over low beta frequencies, you get 1 dot per patient. And here on the y-axis, you can see the UPDRS, which is a clinical score and which indicates you how affected the patient is in his motor symptoms. And you can see that there's a correlation between the amplitude of this beta signal and the motor symptoms, which is quite interesting, I think, or amazing, because we're in a very, very small area of the brain, and we averaged over many dimensions, and we just get 1 value that is the beta power, and it correlates with such a complex phenomenon that are all the Parkinsonian motor symptoms that are captured in the UPDRS score. So really, in this case, a lot of meaningful information is already contained in 1 modality, and you didn't need multimodal. I mean, multimodal always explains maybe more, but still 1 modality explains a lot already. But still, what you may have noticed now is that, okay, we lost the time domain, right? Because what we observed in our raw data was that there is indeed more periods of high amplitude activity in the beta range. But even in the on medication state, you can see those yellow droplets here that are distributed across the recordings. And you can also see in the off medication state that it's not a straight line that is continuously elevated, but that there are more regular droplets and longer droplets of periods where it's increased. So maybe it might be interesting to look at your data and to perform dimensionality reduction in another way. And you could think of maybe doing this by first, instead of averaging over the time domain first, instead of performing the dimensionality reduction first on the time domain, you can average over frequencies. So your frequency of interest would be the low beta band. You would average over the over this frequency band, so you lose your exact information on the frequencies. You focus on the low beta frequency, but you still have the time domain. And what you can see is here now the evolving amplitude of the beta signal. And it's just another way of visualizing what you already saw here in this time frequency plot. That is, you have brief periods, so-called bursts of high amplitude events in the beta range, which would be beta bursts. And you have them also in the off medication state, but if they occur, they are prolonged. So now you want to see whether this time domain is relevant for or has an impact in this difference that you observe from the on to the off medication state, and you reduce the dimensionality by averaging over time, just checking whether the time that beta synchronization occurs differentiates between off and on medication state. And indeed it does. So these periods, these beta bursts are longer in the off medication state than in the on medication state. And again, averaging this per patient, so the average burst duration in the off medication state explains actually more variance in Parkinson's motor symptoms than beta power. So just by looking at your data in another way and performing the dimensionality reduction from a different perspective, you can explain more variance in this complex motor symptoms that you can observe in Parkinson's disease. But now moving to the second dimension, that was the dimension whether the patient is at rest or during movement. We can record local field potentials of the subthalamic nucleus while the patient is moving. So here, for example, you can see a movement trace of a patient that moved a rotatory handle continuously over approximately 30 seconds. And in parallel, you record the subthalamic local field potentials. And what you can see or visually perceive in this raw data trace is that while the patient is moving, apparently this frequency band that we previously identified as being somehow meaningful for motor symptoms reduces its amplitude. So the beta activity is reduced in amplitude during movement and then increases again as soon as the patient stopped the movement. But there might be a second frequency band that is of interest or that strikes you in this raw data, is that the higher frequency range that is called the gamma frequency band, between it's usually defined between 40 and 90 hertz, that seems to increase in amplitude during movement and then decreases as soon as the movement stops. So during movement, there might be two frequency bands of interest that are the beta range and the gamma range. So first, stick with the beta range because we talked about this already. Beta activity decreases during movement, right? So this is what at least our raw data trace suggests. So again, we can average over the time domain and compare two time domains, the rest time and the movement time. And to again reduce our dimensions. And what we observe is, yeah, I think these were 12 patients, over patients, across patients, the amplitude in beta activity reduces during movement when compared to rest. But again, we lost our time domain, right? So then let's perform this, the dimensionality reduction as we did previously. So first, average over our frequencies of interest, which would be the beta frequencies at this moment, and observe how the amplitude of this frequency of interest evolves over time. So again, here you have a movement trace. So when the patient moves, indeed the amplitude seems to drop. But still you have fluctuations in this amplitude. And if you perform this thresholding that we did before to identify periods of high beta amplitude, of beta bursts, then you see that even during movement, the low beta activity crosses this threshold sometimes. It's not continuously suppressed below this high beta activity periods, below the beta burst threshold. And indeed, what we can see is that the rate of beta bursts is reduced during movement, but they still occur. And if they occur, then they explain some of the variance of movement speed. So here in this movement trace, for example, you can see that the movement velocity is higher at the beginning and then decreases during approximately during the times where this beta bursting increases again, and then the velocity slightly increases at the moment where we have less beta bursts. So the time spent in beta burst during movement seems to explain some of the variance that we see in velocity decrease during a continuous movement. Now moving to the second frequency band of interest, that would be the gamma frequency range. Remind ourselves here, you see an increase in gamma activity during movement. And to assess this gamma activity, we performed a study where patients actually didn't do continuous movements, but did single movements. And this means that we had three trials. We had small and slow movements, medium movements, and large and fast movements. So we added another dimension to our data. We have four-dimensional data now. And what we did first then was to reduce this last dimension by averaging over trials. And then we have our time frequency plots that are aligned to the start of the movement and that are averaged across the movements that were small and slow, and averaged across the movements that were large and fast. And again, what you can already visually perceive here is that this gamma synchronization is observed in all three cases, but it increases with movement velocity. So gamma activity seems to scale with movement velocity. And interestingly, when you average over this last part, so over the large movements, the relative change of gamma activity, this relative increase of gamma activity inversely correlates with motor symptoms. So it seems to be a prokinetic signal if local field potentials synchronize a lot in the gamma frequency range, then it's associated with less motor symptoms. So patients that are that move faster and have less symptoms of Parkinson's disease, which would be mainly slowness of movements and stiffness of muscles. But again, we lost some of our informations because we averaged over all trials, and we don't see the exact temporal dynamics of this gamma synchronization during trials. So if we're going back a step and we're looking at all those large amplitude trials, and we average over our frequency of interest first, the gamma frequency range, then what we can observe here is that at rest, these amplitudes of the gamma frequencies are low, and then they increase during movement. But again, they're not, although this is suggested here in this plot, they're not continuously increased, but they rather increase in small bursts as well, in gamma bursts. And when you average across these trials, you get this seemingly continuous synchronization that is a phenomenon of averaging across trials. So when comparing baseline, so rest to movement, then you see an increase in this rate of gamma bursts. So you can have gamma bursts at rest as well, but they're much more frequent during movement. And this again is also modulated by dopamine. So when patients have no dopamine in their system, so in the off medication state, this rate of gamma synchronization is reduced when compared to the dopamine substituted state. And it is this rate that also, again, seems to explain more variance in the motor symptoms. This time it's inversely correlated in contrast to beta, than beta power. So looking at your data from a different perspective, again, seems to capture more meaningful data than when averaging over the time domain. So I'm already at my, already after 30 minutes of talk, at the summary of the content of my talk. that would be on subthalamic local field potentials in Parkinson's disease. And the main message that you might remember from this is that subthalamic local field potentials are modulated by dopamine and movement in various frequency bands. And when we concentrate on the beta frequency range at rest, then without dopamine, we see an increased amplitude of beta activity when averaged over time. But this increase of amplitude is not present continuously, but rather occurs in bursts of increased amplitude, and this burst duration correlates with motor symptoms in Parkinson's disease. During movement, subthalamic beta oscillations decrease in amplitude when averaged again over time, but even in these periods of decreased amplitude, you can have beta bursts, and if they occur, then they correlate with the velocity decrease. And then lastly, the second frequency band of interest, that would be the gamma oscillations that increase in amplitude during movement. And this increase scales with velocity, but again, it isn't present continuously, but occurs in gamma bursts. And this gamma burst rate during movement inversely correlates with motor symptoms. So main message again, time domain seems to be important. And the summary from a broader perspective would be that one modality can contain multiple dimensions, and that different modalities such as imaging, electrophysiology capture different properties of the brain in the space or in the time domain, for example. But that one modality, as I said, can contain multiple dimensions such as time, amplitude and frequency, and that various forms of dimensionality reduction can provide meaningful information. So to come back to my river image, I think my main advice would be that it's always good to look at your data in many different ways. Thank you.
Thank you. Thank you so much, Roxanne. I have to say that I'm quite impressed of your teaching and presenting skills. Honestly, you provide the right enough details, like no more, no less, and you give a comprehensive image for what you're talking about. The ideas looks very understandable.
Thank you.
Thank you. Julian, do you want to take?
I completely agree. Yes, really amazing talk, especially also the river comparison is very intuitive for everyone, I think, and a great idea. So I think I'm not sure whether the people were clapping or whether they were putting their hands up. Ah, okay, it was clapping. Okay, so please feel free to step up if you have any questions or put in the chat. Jonathan is already ready.
Hi, Jonathan.
Hi there. Thank you so much for your talk. I mean, I have no background whatsoever in local field potentials, but the way you explained this frequency and time domain and these type of transformations you need to do in the data was really, really amazing. There's only one point that I missed a little bit of understanding, and that's like in the slide you explained the velocities, like the small, large, and medium velocities. Mm-hmm. Could you explain again what exactly the participant needed to do in order to measure this velocity?
Yeah, I can show you maybe some data that explains it. Actually, because this was a study that was published, and do you see my screen?
Yes, we do.
Yeah, so it was published in eLife, and eLife, they offer you also to make a video of your data. And
we don't hear the sound, Roxanne.
Ah, okay, sorry. So this was the task that patients were performing, right? So they performed single movements with the rotatory handle. And So they either performed, it was visually cued, they either performed a small or medium or a large movement, and there is a coincidence of association of amplitude and velocity. So small movements were always performed slower than large movements. So this movement would always be slower than this movement. And we then aligned actually the frequency or the gamma synchronization to different time points. For example, the time point of maximal amplitude would be this one, while the time point of maximal velocity would be during the movement, right? And what we saw was that gamma activity actually synchronizes most at this time point where you have the maximal velocity and not at the time point where you have the maximal amplitude of the movement. This was just a way because in Parkinson's disease, movements are always slow and small. And it was just trying to disentangle those aspects of movements, amplitude and velocity.
I see. Well, now I saw the video clip, I can imagine what exactly the task was. I mean, I was wondering in which extent you are actually correlating the observations you saw with velocity of movement, or just the distance you're trying to move things, or moreover, the energy you anticipate to need to do a certain movement. Because I'm not sure whether you agree, but in this experiment, you cannot disentangle the distance, velocity, and energy because you're just rotating a handle.
Yeah.
And those are of course very much correlated.
Exactly. So amplitude and velocity is correlated, as I said, and the way of disentangling this would be that the time point is a different one. So the time point of maximal amplitude is a different one than the time point of maximal velocity. But so this was the way how we addressed this. But of course, you cannot completely disentangle it in this task. And what is interesting, what you mentioned, is this effort component, right? So you would think that a movement that is large and fast requires more effort than a movement that is small and slow. I know that Peter Brown's group, and mainly it was a study of Hui-Ling Tan, assessed this or created a task where they disentangled the effort without having different motor output. And indeed, they suggest that it's effort that is signaled through subcortical gamma oscillations rather than a specific motor output.
Okay. Oh, interesting. Okay, thank you very much for your comments.
So there's another question. Yeah. From Shafar, you want to read it?
I could. Atif says, thank you, great talk. Mansour said, great talk. Wonder how these findings differ over the different contacts of the local field potential. Do you see similar activity for similar contacts, or do you typically pick one optimal contact based on anatomy?
Yeah, so exactly, a very good question. I think this is one multimodal moment then of my research, is to integrate both this neurophysiological data with the anatomical data that we get from the electrode reconstruction, where we know where the electrode exactly is located. And is there a way, because there's a figure also in this paper, but I don't have it right now. So it shows that the gamma synchronization actually is not equally distributed across contact pairs, but it is localized within the subthalamic nucleus, and it really peaks at the dorsolateral border of the subthalamic nucleus, which is the motor part of of the STN. So in these cases, we didn't perform a best contact pair location. We just averaged across contacts, but of course you can perform best contact pair selection by looking at what contact exactly your gamma synchronization would be highest. And I'm just checking whether I can show you this figure. Because it might.
So can you not see it? I think I tried to share it already on the screen.
Okay. Yeah, sorry, I was on. Yeah, okay. So this is exactly the figure. So what you can see is that this gamma synchronization is highest in the dorsolateral border of the STN if you localize all contact pairs of all 16 patients that we had and that we recorded of in this study. And that again, you have this scaling that is also confined to the dorsolateral border of the STN. So here you integrated two modalities, right? Neurophysiology and anatomy, or not anatomy, but imaging.
And that includes all channels recorded, right?
Yeah, exactly. So this includes, so per patient, you have 3 channels that you record off, and we plotted then the exact location within the MNI space and of all 16 patients and looked whether there is a distribution in gamma synchronization across the patients and across all contact pairs then.
Okay, I think there are more questions.
Yeah, I had another question, and that was related to the pathological beta synchronization you have in Parkinson's disease. Maybe you can just comment how you disentangle this for movement and also for bursts. Do you rate for that if there are different contributions of beta for different disease states in Parkinson's disease?
Sorry, can you, sorry, I didn't exactly get what was the question again. Can you try to formulate?
So it was shown that in Parkinson's disease, there's this pathological beta band. And this is exactly also the scope of the research that you presented. That you looked at the beta band fluctuation that is different to movement. And how do you account for the different pathological beta synchronization, and how do you distinguish that to movement in general?
How do you know this is what is Parkinson specific and what is simply physiological movement signals?
Yeah.
Yeah, of course. I mean, we cannot exactly disentangle what is pathological and what is physiological, because we don't have the physiological state, right? And in this study, we recorded only in patients without dopaminergic medication, so they were in a pathological state. But what we did was to look whether there are frequency-specific contributions. So we separated the beta band and the low beta band that is always suggested to be the pathological range of beta activity in the high beta band, and there were also beta bursts, high beta bursts during movement, although they were also reduced, but they did not explain any of this velocity decrement that we saw during the continuous movement. So we had this frequency specificity, and then of course you can say, okay, but maybe if I'm continuously moving, then I'm also just dropping in velocity over time because of fatigue. We cannot correct for this, of course, but it's a very specific symptom for Parkinson's disease that over time and already after the first movement, actually, you can have, you see a reduction of movement velocity and amplitude. It's called bradykinesia, right? Bradykinesia is a composition of slowness of movement, but also of the decrement of the movement, so that the movement reduces pathologically in amplitude and velocity over time. So as this is a quite pathophysiological or pathognomic, it's really a pathognomic feature, because this, for example, in a clinical perspective, it's the way how you disentangle different hypokinetic movement disorders, is that you may have movement disorders where people move slowly, but it's only in Parkinson's disease that you have this very typical observation that the movement is not only slow, but it also decreases in amplitude and velocity. And this again might be some kind of lack of effort signal, right? So it's maybe back to Jonathan's question that the basal ganglia are needed to signal this reward and this that you want to perform a small, fast movement, and this reward signal or this effort signal then is reduced, may be reduced in Parkinson's disease due to the lack of dopamine.
Okay,
Don't know whether it was the precise questions.
I have another question to you, Roxanne. Or Jonathan first, please.
Yeah, actually, I thought Timon's question was really, really interesting because you mentioned the difference with other diseases as well. I have no idea whether this exists or whether you can comment about that. But if you assume that the dopamine, if patients with Parkinson's disease are on dopamine state, may not still be the same as just healthy aged individuals, what would the local field potential recording in healthy aged individuals look like in comparisons with Parkinson's disease? Do you know whether this exists, or is this impossible to? Then you would be able to disentangle which part is just normal physiological and which part is pathophysiological, right?
So, I mean, this is deep brain stimulation is very invasive, right? So you implant an electrode in a brain, which is, I think, for me, the most invasive thing I could think of. I know that now with Elon Musk, a lot of people apparently want to have electrodes in their brain, but so far we don't have healthy people, and I, as a medical doctor, wouldn't implant electrodes in a healthy brain. So we don't have the healthy comparison, and we already we always say that substituting dopamine would be really getting a system close to the physiological state, as in Parkinson's disease, it's actually the only thing that is missing, right? It's dopamine. So if you contribute dopamine, then you would think, okay, this is quite close to physiological, but of course not entirely close to physiological. And then what you can do is compare to other disease entities where you have deep brains, where you perform deep brain stimulation because it helps people, but maybe not in the motor domain. So you would have, for example, psychiatric diseases such as OCD, where sometimes you implant deep brain stimulation electrodes also in the subthalamic nucleus, and OCD patients wouldn't have movement disorder, so maybe at least in the motor domain you would have a physiological signal. But these are very rare cases, and we didn't have those as comparison group.
Okay, thank you very much.
I have another question, but I want to show this first to Jonathan, because Roxanne, what you didn't mention is that you actually did that.
Yeah, but not for movement. This is rest data.
Yeah, that's right. True. So this is comparing the beta activity between dystonia and Parkinson off and on, and you can clearly see a difference. Anyways, so my question was more, given that you have now just submitted a paper with data from 100 patients.
99
patients. That is probably, or I really believe this is probably the single paper with most patients reporting local field potentials in the world. And I wonder what your comments or ideas are that make working with so many data sets easier. So what do you think is the most important aspect for you in the way you structured your data that made it easy to work with all these data sets? Which metadata, what do you need to perform this analysis?
So I think one more abstract or less precise thing is really that I think it's really important, and this is what I try to highlight all along this talk, is to know the data. So to know what it contains and how many dimensions are within this data, to think of how to best structure it and how to make it accessible. So of course, organizing data is an entire research field, and therefore there will be or are already specialists for this part. But I think the communication is very important to really know what is exactly how many dimensions are contained in data so that you can store them accordingly. I am, of course, this typical researcher that has big chaos in his or her data, but I think what I always did was then just create structures within MATLAB files that contained all dimensions and informations that I needed.
Okay, so that.
So I have one MAT file for those 99 patients, for example.
That's great. That's the advantage of having only a few channels, right?
Yeah, exactly.
So ultimately, I think that's also a nice perspective that kind of goes against all the other talks, is that no matter the...
I go against the other talks? No.
Yeah, of course. You're saying you really, not only, Stefan also said the same, I think. You and Stefan, who are both people who, no, it was Joaquin, I think it was, sorry, it was Joaquin. Both you and Joaquin are people who work with a lot of the data sets. And they both said the most important thing is to know the data. And actually then it doesn't matter how the data is structured, right? So ultimately all the standardization effort and things are not so important if you really know your data. So that the question is like, can you take work off the researcher who would like to get to know their data? And what would the steps be that would help the researcher in getting to know their data?
I think there's no way of taking this from the researcher to get to know their data.
That's my point. Yeah,
and
exactly.
to look at their data and to explore their data, because I think we have a very, maybe this gets a bit spiritual now, but I think the learning of our brain and how we work is a lot of on experience, and you have to get experience on your data as well. So you have to swim in it, you have to look at it, and you have to explore it. So this is a very important part of research, is really to look at the data, but still, of course, there can be a lot of help that this data looks nicely. So all channels have same names, all structures are, as for example, in SPM files are structured in the same way. And this, of course, allows you to explore your data, is that you don't have to check every time, what was the name again of this channel, and was it a structure, or was it a matrix, or how was it organized? This is, of course, meaningless thinking in the sense of exploring data, but still looking at your data, there's no way, I think, to avoid this for research.
Oh, okay. But now you mentioned channel names and some structures. Are there like very specific things that you need to work with local field potentials for those who don't know about this? In addition to channel names, what do you need to do your analysis?
What I need to do, sorry, I maybe...
So I think, like you mentioned, that you have so many different dimensions in your data, and it is important to reduce dimensions, but you also need to have some of the information at hand, and that's what you just said, like channel names. And I just wanted to add to this discussion maybe few more specifics for people who do not work with that. And from my side, I think having for every channel the electrode localization in the standard space is very important. I think knowing the sampling rate,
okay. Sampling rate
any other points for you from your side? What are
Yeah,
the
of course, that your structure or where the data is stored contains the information on the sampling rate, on the pre-processing that you did, on the smoothing, for example. All those things, specifically if you're interested in the time domain, can be relevant and should be always contained in your final structure and not get lost. So these pre-processing steps, I think, should be contained. Then, of course, the imaging data that you may have, such as MNI coordinates, but also then in a broader sense, the connectomics as well. Yeah, of course, the task information too. So that you can reconstruct your raw data from your pre-processed file.
Okay, great. So I'm going to try to write up all the things that we named exactly, and because we're going to implement standards, right? And we will need not only a concept, but also very specific points that we have to write down and make sure that in our collaborations they are available for all the researchers.
I think Jonathan will have this position, right? So I think it's really an important part of it is to meet the people and to talk about their data, because I think when I'm swimming in my data, sometimes I lose vision of it. And when I'm explaining it to someone, then I realize again what are the important parts of it to convey the information that I'm actually looking at.
Exactly. I wrote down some of the things you said about this type of thing, but the problem will be that a lot of different researchers have different ideas of how a nice standard will look like. Find a common page in which everybody finds a logical structure in this data is actually quite challenging, because everybody has their own experiences in how things need to be. For instance, I absolutely don't like the fact that all 99 patients would be in one huge math file or something like that. I would prefer 99 separate math files, but to which extent is that just personal preference, or is that just a way of organizing the data? It's an interesting discussion, I think.
Yeah.
Yeah.